Welcome to this video on the Biot-Savart Law. In this video, my main objective is to present a simplified, or really a specific version of the Biot-Savart Law. So if you're looking for a much more rigorous calculus derivation of the law that can be used in multiple different circumstances, you want to skip ahead to videos 10 and 11 where I cover that information. In this video, like it says, we're looking at a simplified version, or rather a very specific version of the law that's a good approximation that you can use if you're in an Algebra Based Physics course, which is what this is being presented for. So, what the heck is it? What is Biot-Savart? Well, it's actually the hyphenated two last names of two physicists, Jean-Baptiste Biot and Félix Savart. And we're not going to get into them at all, but the law is named in honor of them, and it's really the math behind the idea that was presented in the last video, video 8, which is the idea that a current carrying wire produces its own magnetic field. Now, it's important to note not only a current carrying wire produces its own magnetic field, in fact any moving charges do, so just keep that in mind. So we're going to start with this whole idea here, is that we're looking at fields again. Now the other fields that we've looked at before, there's two of them. We had the electric field, which the equation we established for that was 1 over 4 pi epsilon naught times q over r squared. The gravitational field equation, which was universal gravitational constant times source mass over r squared. And now we're looking at the magnetic field equation. Now, in a basic sense, we're going to get this r squared relationship again between B and R, like we have between E and R and G and R. However, by the end of this video, because we're looking at a very specific or simplified version, it's going to become just B versus R instead of R squared. Now we're going to eliminate the gravitational equation from this video for right now, because we're really looking at electromagnetism. And the idea that we're going to hopefully establish by the end of this video is fundamental to our understanding of electromagnetic waves, also known as light or radiation. So it's extremely important, attributed to James Clerk Maxwell for kind of tying it all together. So let's jump right into it. I'm going to do a little experiment here that should hopefully support some basic structure that looks very similar, because after all, the electric and the magnetic fields are very closely related to one another. So what I'm going to do is, I have a circuit here where I have a battery, I have an ammeter to measure the current so I can get some data. I have this, which is a potentiometer, which is the fancy way of basically just saying a variable resistor. A variable resistor is of course a resistor that can vary its resistance. Not a very creative name, but easy to understand. This over here is actually what we call an inductor, but in this case I'm not really using it to describe or harness its inductance, but more so just to produce a lot of wire. Okay, now what this is, if you think about it in just layman's terms, there's some sort of central pipe or shaft or something, and you can think of maybe a PVC pipe, and around that we've wound a whole lot of wire around that, and then you connect one end of the wire to the circuit and the other end of the wire to the other part of the circuit. So really the reason that I'm constructing this or using this inductor-like element is because I need to overlap or superposition the magnetic field. So let's just remember that term again. Superposition is the fancy way of saying overlap, and what I'm trying to do here is overlap the magnetic field, and if you think about it, it would be like strengthening the magnetic field by however many wraps I do. They overlap, overlap, overlap until I have a field that I can actually measure something with. Okay, great. So now I want to do measurements of magnetic field versus current. Because if a magnetic field is produced or comes about when a charge moves or there's current, then maybe as I make the current stronger, the magnetic field should become stronger too. But how are we going to measure the magnetic field? Well, what we're going to do here, let me make some space, is in order to measure this overlap, I'm going to use a Hall sensor. Okay, here's my version of a Hall sensor. This is really what we talked about in video 7, which is a magnetic field sensor. It kind of looks like a pen in a lot of cases, and there's a wire that will connect it to our computer over here, and that will take readings of the magnetic field at any given time. So what I'm going to do here is vary the resistance. Now as the resistance, let's start it at a high resistance, and we're going to slowly lower the resistance. As that happens, the current should increase, because remember that my relationship between current is an inverse relationship to the resistance. So as the resistance value increases, the current will drop, and vice versa. So remember, if you don't do the linearized graph, it looks like that. All right, so what I do here is set the resistance, measure the current, measure the field, plot a point. Change the resistance, the current changes, the field strength changes, measure another point. Repeat, repeat, and I start to see something lovely to behold, which is a linear shape. This is a constant rate of change, which is great because that means that I don't have to linearize anything, and it should actually make my life a lot easier when I'm trying to figure out what all the constants mean here. Now remember, very important idea is that the constants of the math function, okay, so this is this generic math function idea, are going to represent and show the constants in the experimental process. So this is really important. What was held constant in the experiment will show up as a constant in the mathematical function. Well, if you think about this, I didn't tell you, but inside the PVC pipe, I'm going to put the magnetic field sensor in there so that I can get a nice overlapped reading. Now the whole experiment, notice I didn't move the magnetic field sensor. So the value R, the position of the detection, was constant. So I would expect that if R is related to the magnetic field, like if I measured here versus here versus here versus inside, I'd get different values, that if that was held constant, it should show up as part of the constant of the experiment. Okay, let's see if that actually worked out. Well, if you actually do measure this, you do see that relationship. Here's where things are a little bit different to the electric field. So whereas the electric field, we saw, let me write this out again, we saw an inverse square relationship with the field strength. In this particular case over here, we see that the magnetic field is going to be a direct proportion with the current, right? Because if I write my generic linear function, I know y is the magnetic field, represented with B, x is the current, represented with I, and then I have this constant stuff in here. So what I see is that I is analogous to Q, but instead of R squared, I'm actually getting R. And this is, again, because I'm in this simplified, or this, it's not really simplified as much as it is specific case. And this specific case is, we see that R is not squared, but it still has that inverse relationship. So that's great. We have this in here. So part of the slope is 1 over R. But it turns out there's more involved there. So let's go ahead and look back at our old electric field equation. We have this epsilon naught. Remember, this was a material or a spatial descriptor or constant. And then we have this 4 pi, and if you look back on the old videos, it was 4 pi r squared. We kind of grouped those two things together because it is constant in this case, right? So if we think about that, if you remember, we had a point charge. This is just a little sphere, okay? It's a little sphere that has some sort of charge value, and we said at any position on the surface of an imaginary sphere, just to kind of imagine like any point you pick on that surface area, remember the surface area is going to be 4 pi r squared, you get the same electric field equation. So you would see that if you were graphing E versus Q, you saw that the slope would have to give you 1 over 4 pi r squared, which is that surface area, so there's some geometrical component to the measurement here, and then the epsilon naught was describing the nature of the space around it. So when we come to this magnetic field equation, we're going to do something pretty much the same. There's going to be some spatial value, and there's going to be some geometric component to the situation. But instead of being a surface like this, let's take a look at the wire again. Okay, so if I kind of cut out a segment of wire here, let's say that's the piece of wire that I have, say that's just cut out from right over here. There's current running through it, and I measure the magnetic field. We know from the last video that the magnetic field shows up at the same point, or shows up as the same magnitude at any point along this path. So at the same R value away, we get the same magnetic field strength. So here, instead of being a surface, it's a circumference, which is 2 pi r. So we're going to come over here and say that in my slope of this equation for the graph that I've just come up with, where I'm doing B versus I, that part of my slope is going to be 1 over 2 pi r. So it's lining up with the electric field equation pretty well. One thing that has changed is this r squared, and this is an r, but that's just for this specific case. And then we are missing this material or spatial component. Now remember, for this, we had named this constant the vacuum permittivity constant. But for magnetism, it has a very close cousin to this, and this is actually, instead of epsilon naught, it's going to be mu naught, and mu naught is known as the vacuum permeability constant. So you can see here that these two things are very closely related, and the relationship between mu naught and epsilon naught, this ratio, is a very, very profound connection that we'll talk about much later on. But here's the equation. That's the answer to this whole video. And that is that the magnetic field around a current carrying wire can be defined as the constant mu naught over 2 pi times I over r. And we just pull the r over here and the I over here because these are two things that can be varied, but the mu naught and the 2 pi are fixed. So this is a special case, or a specific or simplified case of the Biot-Savart law.